couple of comments based on the first night's homework, which was very good. I was very pleased with the effort and with the results. Everybody was 80 to 90% correct in things with just a few errors. There were a couple of things that people didn't understand well, but I anticipated that. Okay, however, a couple of things I saw. Okay, one, what's wrong with this picture? Okay, stop and think about that if you don't remember. Well, you should pause until you see what's wrong with that picture. But what's wrong with it is that these are not equal intervals, but they are marked as equal intervals. In other words, the interval from 1/2 to 1 has a length of 1/2. From 1/4 to 1/2, the distance is only 1/4. From 1/8 to 1/4, the distance is only 1/8. So we have equal markings for unequal distances. If this is marked correctly, and it's very easy to see this, we put 0 here and 1 here, and then we subdivide. We got 1/2 here, and then we divide that in 2, and we have 1/4, and divide that in half, we get 1/8. So we do have two equal intervals here because we didn't go below 1/8. In other words, this interval is equal to this one because we got this by dividing this interval in half. Okay, so be sure that you don't represent unequal quantities with equal intervals. Make sure that you scale your graphs carefully. The problem that this caused was we know that the pendulum period graph looks like something like this. Okay, it's decreasing but at a lesser and lesser rate. And if you do it like so, actually the graph ends up looking like this. And that's clearly not representative of the way the period of a pendulum changes, or the time between counts on a pendulum changes when its length changes. Okay, so that was the context of this thing. I saw a graph here by somebody who's doing very good work that just, how did that graph occur? Did she reverse the coordinates? What happened? And then I just took a good look at the axis and I saw what it was. This is not an uncommon thing. I'm sure I did that at least once in my life in high school. So don't feel badly, but be alert for that sort of an error. Okay. Another thing came up on homework. We had the question of whether, and let me just write a little something to the board here. Now, in relation to a question of whether it would make sense to add the point 0, 0 to a certain graph, the comment was if you start doubling x and tripling y, beginning at 0, 0, the student said you would get a horizontal line because tripling y, well, y would never increase. And that was a really good insight. The only problem with that insight is that x wouldn't increase either, because, of course, x is also 0 when we at the origin. So that tripling 0 always gives us 0, doubling 0 always gives us 0, so that if we double x and triple y beginning at 0, 0, we never get anywhere. Now, that doesn't necessarily say that adding 0, 0 to the graph doesn't make sense. Okay, in a certain sense, of course, it doesn't. In a certain way, it doesn't make sense because obviously if you start doubling and tripling from 0, 0, you never get anywhere. But in other ways, maybe it does. This doesn't say that this doesn't prove that it doesn't make sense to do that. So you want to give that a little more thought. I'm not going to say too much about that. That's a problem I want people to think about. Okay. Now let's see. I'm trying to remember what those numbers represented. Okay, yeah, I remember. What these numbers represented was measurements students got on a triangle that I had around the room. Okay, everybody measured the same triangle with rulers of the same size and got these results: 13.9, 13, 13.1, 13.1. I measured it, and I got 12.97. Now, I commented that the ruler is only marked down to tenths of a unit. so that 12.97 goes a little beyond what you can say based on the units. I could see clearly that the edge of the corner of the paper was a little closer to 13 than it was to 12.9. And having long experience in this sort of thing, I'm reasonably confident that 12.97 is about right, although if it was 12.96 or 12.98, I wouldn't be all that shocked. Now that's the best measurement I can get with my eyes, which worked pretty well. I think maybe I used my glasses at the distance anyhow that I was measuring. Had I used a magnifying glass, I probably could have estimated that maybe with some confidence to the nearest tenth of a marking. Now my point is that these measurements are clearly not the best possible measurement you could make with that ruler, which it was basically a full-size ruler where your smallest markings were in millimeters, and you can certainly estimate the tenth of a millimeter. Maybe not quite as well as I can, maybe better. You might have better eyes. You might just be better at this. Also, 13 is not a very good measurement when you already have tenths of a unit marked on your ruler. You would certainly at least want to measure to the nearest tenth of a marking. But we want to go beyond that to estimate the next significant figure. Even though it's not completely reliable, it's going to tend to give us better results, better consistency, smaller percent error than if we just ignore that process of estimating. Also comment that maybe that 13.9 should have been a 12.9. Maybe somebody just got a little careless in reading that, because I don't think anybody would be that far off in the reading. So I suspect that was really a 12.9. And then that's, the range of these estimates is pretty consistent with the measurement I get to. There appears to be some ambiguity in our use of the word factor, at least in understanding of how the word factor is used in stating certain problems, especially in relationship to the graphs. So let's just start. The factors of 12. What are the factors of 12? Well, people quickly told me 2, 3, 4, and 6. People understand what factors are. It's the usage of the word factor that's maybe a little confusing. So we can see from this, and I just wrote this in, that factors are involved with multiplication and division. Okay, so the whole concept of factor, it's talking about multiplication and division, not addition or subtraction, not roots or powers. If I have a graph like this where x doubles, I ask by what factor does the y value change? Okay, now the factor by which the y value changes, well, let's go over here first to an example where we did a factor that was equal to 3. That is, we did the graph where y triples whenever x doubles, so that we have an x here that's doubled and a y value that's tripled. So the factor is 3. That is, y changes by a factor of 3. So I can write y changes by factor 3 when x, not y, doubles. Now, by what factor did y change here? You might have read it, but ignore what you read. Can't really do that, can you? Okay, well, y gets bigger, so the factor is bigger than 1. Okay, it doesn't double, because if y doubled, you'd be all the way up here by the time x is doubled. Okay, so the factor is between 1, which would indicate that the y value would be here, and 2, which would indicate a y value up here. What is that factor? Well, if I use my fingers, I can say, okay, let's just test this. This difference here appears to be right at half of this value, which means that y changed by a factor of 1/2, but that the second y value is therefore 1.5 times the first y value, so that the factor is 1.5. Another way to look at this is about 150% of this. Down here, this is about 300% of this. And if you think in terms of percents, that might be helpful. What's the factor in this case? Well, y goes from this to this when x doubles. So the factor is about 1/2, if I've drawn these reasonably well. Okay? In other words, this is about 50% of this, about 1/2. That's the factor. So the factor, another way to say the factor, what a factor is it's the ratio of the second quantity to the first. Now I could write all kinds of qualifiers around that, but from the context of what we're talking about, it should be clear what I mean by that. Okay, and I have down here related. We can think of the second quantity as a percent of the first. So again, this is 300% of this. Here's your first y value, here's your second. Here's your first y value, here's your second. It makes good sense that this is 150% of this. Here's your first y value, your second. This is about 50% of this. Now, in relation to pendulum counts, we have data that should be familiar to you. Pendulum of length 1, then 1/2 of that, then 1/4 of that, then 1/8, and we don't worry about what this unit is at this point. We're just testing the nature of the relationship between the time between counts and the length of the pendulum. These are the times between the counts. Okay, we have 0.28, 0.41, 0.57, 0.82. Now, if we go from 1/8 to 1/4, the time between counts goes from 0.82 seconds to 0.57 seconds. Okay, that's a factor of what? Well, it's less than 100%. 0.82 is bigger than 0.57. To find the factor, we just divide 0.57 by 0.82, we get 0.7. So that 0.57 is about 0.7 of 0.82, about 70%. If we do the same thing with these other numbers, the 0.41 divided by the 0.57, 0.28 divided by 0.41, we again get factors that are very close to 0.7. They probably range from maybe 0.68 to 0.72 or something like that. So it's very plausible that for this data we do have a constant factor. So that doubling the length of the pendulum changes the time between counts by a constant factor.